Okay, this is a brief introduction to our matrices unit. So today we're going to learn what a matrix is, how to add it, and how to multiply. So a matrix is a rectangular array of numbers simply enclosed in a bracket. So it's basically like a table without all of the information on the side as far as labels goes. So we have ham, turkey, and tuna type subs. These are the different sizes. If we were to put brackets around this part, that would be considered a matrix. So some information that you need to know are what is considered the dimension of the matrix. It's always the number of rows by columns. So rows go this way, so it'd be 3 rows, and then there are 2 columns this way. So this is a 3 by 2 matrix. So each entry in the matrix is just one of the particular values. For instance, if I took this right here, this would be an entry in the matrix. And then each entry has a particular address. Just like you have an address for your house, each number in here has a particular address. For instance, if I was going to talk about the address of the value 3.75, I would use, if this was matrix A, we use capital letters for the matrix. Then its address would be little a, and then the subscript tells you the row and the column. So this number is in row 2, column 1. So I would put a 2 and then a 1. That doesn't say 21. It means row 2, column 1. So I'd like you to pause for just a quick second, and I'd like you to write down what is at the location of A12. So find A12. And that would be the 595 because it is in the first row, second column. So first row, second column. Now, I'd also like you to tell me what is the address of the $3.50. So if you look at this one right here, I'd like you to write down what is its address. And it would be A, it's in row 3, column 1. So it would be A31. Okay, a little more practice with this. If I were to write down the dimensions, you always do rows by columns. So think about the number of rows versus the number of columns. So this would be a 3 by 4 matrix. And if I ask myself, what is the entry at M32? That means go to row 3, so row 3, but column 2. So the answer would be 11. And then it says the entry 0 appears at which 2 addresses. So take a moment and write down the address for these 2 locations. It would be lowercase m. Since it's matrix M, we would use lowercase m. The 0 in the top row would be row 1, column 4. And the other one would be at row 2, column 3. So those are the 2 locations. Okay, now we're able to add and subtract matrices, and basically the rule is that you just add and subtract the corresponding entries. So this gets added to this, whereas this would get added to this. So you just add the things in the like spot. But in order to add matrices, they do have to have the same dimensions in order to do that. So something like these you could add because they're both 2 by 2s. These are both 3 rows by 1 column. You can add these together. You can add these together. But if you have something like this that are different dimensions and different layouts, you cannot add those together. So to show you an example worked out, if I want to do C minus A, I'm going to take matrix C. So I just copy that down, 3, 0, negative 5, 2, negative 9, 14. And I'm going to subtract matrix A. Matrix A is 4, negative 2, negative 3, 10, 2, 6. And literally what you're going to do is subtract each entry. So to get my answer, I'm going to do 3 minus 4, which is negative 1. Then I'm going to do 2 minus negative 2. Since I am subtracting a negative 2, that becomes addition. So 2 minus negative 2 is 4. 0 minus -3 is +3. -9 minus 10 is -19. -5 minus 2 is -7. And then 14 minus 6 is 8. So that's what the answer to that would be. If I come up to the next one that says add A plus B, I see that this is a 3 rows by 2 columns. So 3 rows, 2 columns. Whereas B has 2 rows and 3 columns. Well, these dimensions are not the same. They have to literally line up perfectly. So the answer to this would be you cannot do that. So there is no answer for that question. Okay, we can also do something called scalar multiplication, which just means to multiply simply by a number. So you multiply each entry by the number outside the matrix. So for instance, in this case, I have the matrix 2, 0, 1, 5. I'm multiplying the whole thing by 2. So this is like just a massive case of the distributive property. Everything's going to get multiplied by 2. So 2 times 2 is 4. 2 times 0 is still 0. 2 times 1 is 2. 2 times 5 is 10. So scalar multiplication is a way to take data and multiply all of it by the same number very quickly. Okay, in this case, it talks about using scalar multiplication if there's going to be a 20% discount on all of these ticket prices. Well, if there's a 20% discount, that means we're not paying 20% of the total, but we are paying the other 80. So we actually need to take all of these values, so this would basically be my matrix here, and I have to multiply all of them by 0.8. Because if you save 20%, you're paying 80% of the original price. So again, I'm just going to multiply every single number here by 0.8. You just take your calculator and go through and do that, and it would be $120, 100, 160. If I multiply the plaza values by 0.8, and then if I multiply the balcony values by 0.8, I'm going to get these numbers. So again, it's just a lot of distributing all at once to multiply a whole set of data very quickly by a discount. Right, these are some properties of matrices. You can add matrices in any order. So the commutative property says you can add in any order. So matrix A plus B is the same thing as B plus A. The associative property means that you can group in any order. So if I had to add A and B and C, I could do A and B first, then add C, or I could do B and C first, and then add A. It doesn't matter. The additive identity just says you can add a 0 matrix and nothing happens. Additive inverse says if they have opposite entries, you'll end up with 0. Okay, the next thing we're going to take a look at is matrix multiplication. So let's imagine that we have a couple teams competing in a football game. So I'm going to add another row here. So we have 2 teams competing. We'll say that this is Marysville, and we'll say that this is St. Clair. Okay, so in the game, Marysville scored 5 touchdowns, 4 extra points, so the point after the touchdown, they missed 1, I suppose, and they got 2 field goals. Let's say in that same game, St. Clair got 3 touchdowns, 1 extra point out of those chances, and 4 field goals. Now, the reason you see the numbers here, and they do have to be lined up in this way, these are the points that you get for a touchdown, an extra point, and a field goal. So if I want to know what was the score for each team, the math that I would have to do when I multiply these together is I would need to take Marysville's numbers and multiply them by the points. So I'm going to take 5 touchdowns times 6, because each touchdown is worth 6. Then I'm going to take 4 times 1. So notice as my finger goes over in the row, I'm going to go down in the column. So first 5 times 6, then 4 times 1, because an extra point is worth 1. And then 2 field goals gets paired up with the 3 points per field goal. So that would be Marysville is the label here, and then points is the label here. So this touchdown, extra point, field goal kind of cancels out in the middle, and you end up with this on the left side, and this is the unit on the top. Now we would do the same thing for St. Clair. So you take the row by the column again. So 3 touchdowns, 6 points a touchdown. Move over 1, down 1. So 1 extra point is worth 1 point. And then 4 field goals was worth 3 points. So if I do all of that math, what I end up with for Marysville is a total, I believe, of 40. And for St. Clair, I got a total of 31. So again, this would be Marysville, and this would be St. Clair, and this would be their points. So the key thing is multiplication with matrices is a little strange. You actually multiply the row by the column. And as your finger moves over in the row, it's going to go down in the column to tell you the numbers that you need to pair up together. Great, so let's take a quick look at another example of this and see a little bit more detail. So in order to multiply matrices, the columns of A, so the first matrix, if this is A and B, the columns of A has to equal the rows of B. Okay? So these numbers in the middle have to match. And if these match, so those have to be the same number, you'll get a matrix this by this. Okay? So if that doesn't make sense for you in terms of letters, let's look at this example here. If P is a 3 by 6 and Q is a 6 by 2, then if I do P times Q, I'm doing a 3 by 6 by a 6 by 2. And what ends up happening is the 6's in the middle are going to sort of cancel out. They match, they cancel out. And my end result is going to be a 3 by 2 matrix. So my answer will end up with 3 rows and 2 columns. Now, what if I try to switch the order to that? What if I do Q times P? Then I'm doing a 6 by 2, and I'm multiplying that by a 3 by 6. Well, now I'm in a situation where these middles don't match. Not like this one where I had those 6's in the middle. If those do not match, you actually can't do the multiplication. So the answer is no solution. You cannot do this multiplication. The process does not work if those numbers in the middle don't match. So an important thing about that is that, yes, you can add matrices in any order, but matrix multiplication is not commutative. Okay? So that means you cannot multiply in any order. We are used to multiplication being commutative, right? We're used to 2 times 5 is the same thing as 5 times 2. Either way, you get 10. Well, with matrices, that's not the case anymore. Matrix multiplication is not commutative. So you have to watch the order very carefully. Right, I'll continue a couple examples in our next video. Gonna stop this one, and then there'll be just a couple quick examples in the next one.